This is the module 5, that is the second part of the module 5, that is earthquake resistant design of masonry buildings. That we can call it as a module 5b, that is part B, and this is the session 1. So in this particular topic, you will going to see about the particularly the masonry structures are concerned. So let us continue with that first session. So here it is a performance of unreinforced and the reinforced masonry structures are there. Okay, so here as far as the masonry construction is actually the oldest and the most common building technique, together with the timber construction is concerned. The word masonry actually uh, consists of it's a type and shape of the material and the construction methods are concerned. So in general, the masonry may be defined as a structural assembly of masonry units such as stones, bricks, and the maybe some blocks with a binding material known as mortar. A virtual, a vertical two-dimensional structure of such as assembly is known as the masonry wall. Actually, the walls of the masonry buildings and the building itself are designed to be stable, strong, and durable to withstand a combinations of the design loads are concerned. Now, the masonry is a typical composite construction material and which consists of the first one is the masonry unit, second one is the mortar, and third one is the concrete infill or the concrete itself, and or the fourth one is the reinforcing steel. The whatever the masonry buildings have been proven to be most vulnerable to the earthquake forces and have suffered maximum damages in the past earthquakes. Particularly in India is concerned, if you consider the past earthquake like Bhuj earthquake, Chamoli earthquake, Jabalpur earthquake, Khilari earthquake, Uttarkashi earthquake, and Bihar Nepal earthquakes. Whatever these earthquakes are there, so they have clearly demonstrated that the major losses of the life was due to the collapse of low strength masonry buildings, and the loss of the lives could have been minimized up to the optimum by making the earthquake resistance of the masonry structures are concerned. So depending upon the material, the whatever the compositions of in the structures are there in the masonry construction systems, they are further divided into the first one is the unreinforced masonry, consists of masonry and masonry units are there. Then next one is confined masonry, which is consist of masonry units, mortar, reinforcing steel, and the concrete is concerned. And last one is reinforced masonry, which is consisting of masonry units, mortar, reinforcing steel, and the concrete as a infill. Because of the specific characteristics of each constituent masonry material, especially masonry units, it is not easy to predict the mechanical whatever the characteristics of the specific masonry type by knowing only the characteristics of its constituent materials, mortar, and the masonry units. Therefore, it is important for each type of masonry, the whatever the experiment to correlate the strength characteristics of the constituent materials with the characteristics of the machineries usually they are going to be carried out. Now, as far as the machinery materials are concerned, so here we'll be having the five major the materials which we can see it. The first one is the masonry unit, mortar, concrete infill, reinforcing steel and the whole masonry units are concerned. Now let us see it one by one. Now first one is the masonry units are concerned. Apart from the load bearing capacity, the whatever the some aspects which we can consider it when while selecting the most type of the suitable type of masonry units are concerned. The first one is adequate thermal and sound insulation capacity of the masonry. Then second one is especially in case of the external walls are concerned. And the third one is the reduction of the weight of the building in order to reduce the seismic loads. And last one is economy of the construction is concerned. So here in this figure, it shows that the different types of the masonry units. The first, the figure which is shows about the perforated unit, and then hollow unit, and then cellular unit, then horizontally perforated unit. So in addition to that, in order to avoid the local brittle failure, hollow units under combinations of vertical and lateral loads, it is required that the masonry unit to be used for earthquake resistance construction of masonry buildings, and also shall also meet the some requirement, the whatever the requirements are there. So the first one is the units whatever are there, so not more than 50% of the holes, or in general the percentage as compared to the percentage gross volume is concerned. Then the minimum thickness of the shells is to be 15 mm. Then vertical webs in the hollow and cellular units extend over the entire horizontal length of the unit. Then whatever the relatively low minimum, the values of the compressive strength of the masonry unit to be used for the construction of the structural wall are like that. The first one is, let us say that it's a clay unit whose the whatever the FB, that is the compressive strength, which is to be equal to 2.5 megapascal. And suppose if it is a calcium silicate units are there, the minimum whatever the FB compressive strength should be 5 MPa. And if it is a concrete aggregate units are there, then FB is equal to 1.8 MPa is there. And suppose if it is a autoclave aerated concrete unit is there, then here it will be minimum of FB will be at least 1.8 MPa. Suppose if it is a manufactured store units are there, in that cases the minimum compressive strength will be 15 MPa. So these are the some standards which we can notice as far as the strength of the materials of the units are concerned. Next comes to mortar. So this mortar is nothing but a mixture of inorganic binder like lime or a cement, then aggregate and water, which is binds together as a for the masonry units. Sometimes some additives are also added to the mortar to improve its workability or for the other reasons. Then according to the classifications of the different types of the mortars are used in masonry constructions are there. So first one we can say that general purpose mortar. So as per the general purpose mortar is concerned, which is a traditional type of mortar and used in joints with a thickness greater than 3 mm, in which only dense aggregate is used. And then second one is thin layer mortar. So here it is used for the masonry with a nominal thickness of the joint 1 to 3 mm. The thin layers are typical mortars designed to fulfill the specific requirement of the masonry construction is concerned. The next one is lightweight mortar. So it is made up of using some materials like perlite, pumice, expanded clays, expanded shale, or other lightweight materials. So lightweight mortars are also designed to fulfill the specific requirement of masonry constructions and have a dry hardened density which is lower than 1500 kg per meter cube. So next one is the concrete infill material. So a concrete makes of suitable consistency and aggregate side, which is used to fill the holes where the reinforcing steel balls are placed. In case of reinforced masonry is called as concrete infill or grout. According to the specifications, the maximum aggregate size should not exceed 10 mm, where the least dimensions of the plywood is 50 mm, and to cover to reinforcement is between 15 mm to and 25 mm, and it should not exceed 20 mm, where the dimensions are not less than 100 mm and 25 mm respectively. In order to ensure the workability and the pourability of the infill, sufficient water should be added to the mix. However, in order to reduce the risk of the cracking in the infill due to the shrinkage resulting from the loss of water into masonry, expanding agent may be used. The whatever the characteristic strength of the compressive cylinder or a cube strength of such concrete infill, the FCK should not be less than 12 MPa or 15 MPa respectively. Next one is reinforcing steel. The smooth or a high bond or the deformed type of the reinforcing steel with the distinct yield plateau, which is used for the reinforced concrete structure, is also used for reinforced and confined masonry construction also. Especially the shape fabricated type will be a ladder type or a truss type of reinforcement is openly placed in a mortar joint. So whatever you can see it in a figure, the first one is a ladder and the second one is the truss type of prefabricated bed jointing reinforcement is concerned. Next one is masonry. When the verifying the load bearing capacity of the masonry walls and the structure to vertical and the lateral loads, the values of mechanical properties of masonry considered as a assemble of masonry unit and mortar, and not mechanical properties of constituent materials such as masonry unit and mortars are used. Next one is the seismic performance of masonry building during the earthquake. So here many masonry structures will collapse or were severely damaged during the destructive earthquakes. So here the three types of the structural systems are there. The first one is reinforced concrete, second one is unreinforced masonry, and the third one is building composed of the some alternative material like so timber frames or bracings with some infill materials are most commonly used in the masonry structures are concerned. So it is observed that the some of the reasons which may cause the damage of the masonry building during the earthquake are classified as the first one is the inadequate the brick unit is concerned. So as far as then second one is poor mortar, third one is irregularities in the plane and vertical direction. The fourth one is weak load bearing walls. Then fifth one is lack of the vertical confinement, confining the elements. Then sixth one is weak out of the plane response. Then the unconfined wall corners, and then the eighth one is the weak first story is concerned. Then the ninth one is inadequate cantilever elements. So these are the some of the reasons where one can notice the damages of masonry during the earthquakes are concerned. So now we'll see it one by one in detail. The first one is the inadequate brick unit. So masonry materials are whatever they are used in the construction of load bearing walls shall be a natural stone or the solid brick or the solid concrete blocks and the bricks with some vertical holes satisfying the maximum wide ratio defined as per the codes are concerned. Now the minimum compressive strength of masonry structures material shall not be less than 5 Newton per mm square on the basis of gross compression area and the compression strength of natural stone to be used in the usually basements, which should be at least 10 Newton per square. Although the usage of them is improper in bearing wall application, even such slight variations in the shape had some the seismic the damage observations. Even the observations may be heavy damage and collapse of the building in the earthquake regions are generally associated with hollow clay tiles which are used instead of the solid the brick units are concerned. So here in this figure it shows that the collapse of two-story unreinforced masonry building in which a load-bearing wall with the hollow clay tiles were cut laterally. So that is the two floors, how you can see it in the figure. So how they have crushed it during the earthquake, and how they have two stories where get collapsed. So from the figure one can notice. Next one is the poor mortar is concerned. Mortar are to be used in the load bearing walls shall be a lime mortar or the cement in the ratio of the cement, if it is cement, or a lime or a sand in the ratio of 1 is to 2 is to 4, 1 is to 2, 1 is to 4, 1 is to 4 ratio, like that. Means one part of cement or a lime or four parts of sand. So like that they are used. And poor quality of the mud or a cement mortar which may cause the whatever the masonry units which will lose its supports to the floors, which is shown in the figure. In this figure, especially when the mud stone masonry structures are collapsed, were heavily damaged even in a small earthquakes due to poor mud mortar and insufficient anchorage between the mud and stone is concerned. So this structural system should not be considered in the earthquake zones, or some wood structural element should be used inserted in the system adequately to prevent the collapse of the structure. So which in the figure you can see the how this the collapse of damaged masonry units and also the due to the poor mortar during the earthquake is concerned. Next one is the irregularities in the plan and the vertical direction. So load bearing walls of masonry buildings must be arranged in plan as much as possible regularly and the symmetrically with respect to main axis. So in the figure it shows that the collapse of three-story buildings subjected to torsion in the in the opposite of the clockwise. So which the arrow mark and how this twisting has been taken place, so that the three-story building has been collapsed during the earthquake. Next one is the weak load bearing walls. The whatever the ratio of the total length of the masonry load bearing walls in each of the orthogonal directions in plan, that is excluding a window and a door opening, to the gross floor area, that is excluding the cantilever floors, shall not be less than 0.5, where the whatever the important factors which is going to vary from 1 to 1.5 of the total length of the load bearing wall is the main important factors for masonry building damages occurring during the earthquakes. Excessive bending and shear may produce in the plan failures depending on the aspect ratio of the unreinforced masonry elements. Many masonry buildings had sustained a very significant damage to the walls in the form of X, that is the double diagonal shear cracking, a typical type of the weak unreinforced masonry, which is shown in the figure as the unreinforced walls in the shear. So that is whatever the typical X crack which is occurred in the load bearing of the inner wall during the earthquake. Next one is the lack of vertical confinement, confining elements are concerned. So here the vertical confining element should be located at the end of the load bearing walls at the both sides of doors and window opening. Whatever in the figure which shows that two damaged masonry buildings due to the lack of vertical confining elements, side of the load bearing wall next to the joint space which is failed as shown in figure first part, and the door opening was extremely narrowed around the middle of the door height as shown in the second figure. It is due to the lack of the vertical confinement. So whatever the both the figures which are representing the damage of masonry due to lack of vertical reinforcement. Next one is the weak out of the plan response. So here the unreinforced whatever the masonry buildings are there, they are most vulnerable to the flexure and out of plane failure. So if the connection between the wall and floor is not adequately restrained, the whole wall panel or the significant portion of it will overturn due to the seismic excitation in the perpendicular directions to the wall plane is concerned. So here in this figure, it shows that the view of out of plane collapse of load bearing wall, actually the added vertical RC confined elements which will contribute to earthquake resistance of the wall. So in this manner, the out of the plane failure does not easily occur. So whatever the figure is there, so which is shows that the load bearing wall was collapsed in the out of plane directions during the past earthquakes is concerned. Then the whatever the unconfined wall corners are there. So suppose if the another type of another type of the failure will be the formation of vertical cracks at the corners of the unreinforced masonry buildings, in which the wall begins to be form a hinge from the swaying. Failure and cracks at the corners occurred because of insufficient connection between the walls and the floor, which the figure itself it shows that the failure occurred in the bearing wall between the window and the corner. If there were vertical confinement element at the corners, then these elements would have been contributed to the earthquake resistance of the wall is concerned. Now the second part of the figure shows that the separation of adjacent walls due to the connections of stresses at the building corners and the poor connections of the wall. Whatever the two figures are there, it is just because of the collapse of the corner and vertical cracks that also near to the masonry buildings are concerned. Next one is the weak first story. So the first story collapse is a common type of mechanism for the unreinforced concrete structure, such as we can call it as a soft story and weak story behavior. The first story collapse is also occurred in the masonry structures as a because of the limited ductility capacity and poor strength of masonry units. So here in this figure it shows that the first story collapse of a building with hollow clay tiles. So whatever this is there because of the hollow clay tiles is concerned. Next one we can see it as a inadequate cantilever element. A free cantilever length should not be more than 1.5 meter. So this requirement is not enough to describe the inadequate cantilever elements for the masonry buildings. If the component of the ground acceleration is large and a cantilever is a heavy one, the mass of cantilever can be very important parameter for seismic beware. As you can see it in the figure that the balcony is weakly supported due to the window openings in the bearing wall and lack of the whatever the reinforcement concrete or a reinforcing vertical and horizontal element. In addition to that, the corner walls constructed inadequately at the upper story collapsed and applied to the force to the end of the balcony span. So as a result, the heavy damage was occurred in the part of masonry building. Whatever the upper story balcony is there, so did not collapse due to the smaller the dead loads are concerned, or the continuous horizontal bond beams and the absence of the wall which is fallen it during the earthquake. If this unreinforced masonries were confined, then this whatever the damage would almost be prevented. So whatever the figure from this, what we can see it that it is a failure of the occurred around the balcony of the masonry during the earthquake. Next, the from the past earthquakes, yes, some lessons are learned. So here it is summarized about the some seismic behavior of the building during the past earthquake, and they had provided the several lessons, and here some of these points are as like that. The first one is the lack of the structural integrity is one of the principal sources of the weaknesses responsible for the severe damage leading to collapse, and the failure of connection between the two walls or between the walls and roof as well as between the walls and foundation has been observed. The next one is the damage in the walls has consisted of the nearly vertical cracking over the head of the openings, and diagonal tension cracks appears between the adjacent openings, then separation of orthogonal walls, and partially out of plane collapse of a second story wall. Then next one is one of the main cause of the damage has been the absence of bond between the perpendicular walls, causing the separations from each other at the junction, and the consequence of which is the loss of rigid box like actions which enclosures. Then next one is the bond elements in the walls have remained the conspicuous by their absence, and separate inner and outer weights of the wall during the shaking. Then next one is the reason is that the highest rate of the damage in the building has been firstly due to the failure of first and second floor projections, secondly due to failure of ornamental balconies and parapet walls, and thirdly due to the failure of arches or openings, and lastly due to collapse of improper tied gable ends are concerned. Then next thing is regarding the stone masonry buildings with thick exterior walls have also been severely damaged or collapsed because of the poor constructions, but they may be survived or remain intact during the major earthquake when they exhibit excellent workmanship. Then next point is about the walls that are inadequately anchored to the floor diaphragm can exhibit large diagonal cracks in the piers due to in-plane loads. If mortar joints are weak as a lime mortar, the cracks follow the joint. And then next one is the diaphragms that are insufficiently anchored can separate from the masonry walls, causing the wall collapse, or the unencouraged gable ends of the masonry walls are susceptible to this problem. Then next one is the provision of vertical steel or elements in the corner of the building, as well as the existence of horizontal tie beams which will increase the resistance to the earthquake. The next point is a non-structural element must be given proper design considerations for the lateral forces and should be braced or restrained. Then the collapse of many of these walls clearly illustrate this the reason. Next point is related with the potential out of plane failure of non-structural elements such as parapet, winners, gables, and unanchored walls are concerned during the earthquake, which constitutes the most serious life safety hazard for this type of the construction. Then next one is in plane failure lesson. It is failure less common than the out of plane failure, and was noted in many strengthened buildings that the typical shear failure occurred in many of the past earthquakes. In next, the whatever the last point is that in general the buildings with irregular plans experience the more damage than the rectangular type of building. The damage was often concentrated at corner due to lack of the detailed analysis, and that included the effect of odd shape plans. Uh, Here, next, the topic in that is the confined masonry is concerned. Actually, the confined masonry is the construction system where the walls are built first, and the columns and beams are poured in a afterwards to enclose. It is confined the walls. The walls are tied down to the foundation. This is just like a ties which work like a string around the parcel. So what we can see it in the figure. Actually, the confined masonry is construction is similar to the unreinforced masonry except for inclusion of RC elements are concerned, and also the local masons can quickly trained and become the whatever they can accommodate to it, and the marginal increase in the construction cost will be there, and here thereby it is keeping it to be economically which is feasible. So here, this is the confined construction masonry. What we can see how this confining of the masonry constructions are made both vertical as well as in the horizontal directions, like vertical in terms of the columns and horizontal in terms of the beams are concerned. So only after construction of wall, the remaining vertical and horizontal confining is made. So this is all about the confined reinforcements are concerned. Next, here it is a components of the whatever the uh, confined reinforcements is there. So here the key, you can see it from the plinth, a horizontal band, and then the vertical element is like a toothed at the wall which is tied to the column interfaces is concerned, and here the whatever the masonry wall is there, it's a unreinforced type, and whatever the columns and beams are properly tied together, and at the regular continuously horizontal bands are there. So it may be a floor level bands or a sill level bands or a lintel level band or even the slab level is concerned. So what we can see it the confined masonry, and it's a key component from this figure. Now, whatever the advantages are there as far as the confining walls, which will be tied with the beam as well as the columns. So, the first of all, it will improve the wall to wall or a floor to roof to wall connection, which guarantee the better transfer of the whatever the forces are concerned, and also close to box action type of action during the seismic event will be there, and the whatever the greater in plane and out of plane stability of the slender structural walls is concerned. And next one is the enhance the strength, ductility and energy absorption capacity when compared to the unreinforced load bearing walls are concerned. So this is all about the advantages of the confined walls. Then the reinforced masonry is concerned. So reinforced masonry is a construction where the steel is reinforced in the form of the reinforcing bar or mesh is embedded in the mortar, or placed in a holes and filled with the concrete or grout. So by reinforcing the masonry with the steel, the resistance to the seismic loads and the energy absorption capacity may be improved significantly To achieve this, the reinforcement should be integrated with the masonry so that all the materials of reinforcing masonry system act as a monolithic when the resisting gravity as well as seismic the loadings are concerned. So here there are various this one ways in which the steel reinforcement can be used in a reinforced masonry structure system. Basically, here the reinforcement masonry systems can be classified into three ways. That is the reinforcing hollow unit masonry, then reinforced grout cavity masonry, and reinforced pocket type of the walls are concerned. So here in this figure it shows that the first one is reinforced hollow unit masonries are concerned, and the second one is the whatever the reinforced grout whatever grouted is there, it's a cavity masonry is concerned. And next one is the whatever the reinforced pocket type of walls are concerned. So this is all about the how this reinforcing steel masonry is there. And also here the whatever the reinforcing steel in the masonry should be there, it should be a corrosive resistance or protected adequately against the corrosion due to environmental conditions. If ordinary carbon steel is placed in the holes and the embedded in the concrete infill, then it should be protected by concrete cover at least 20 mm in thick, and in case of the dry environment, and 25 mm thick in case of humid environment, and 40 mm thick in case of the aggressive chemical whatever the conditions are concerned. So now let us see about the basics of load bearing masonry. So here it's very important to note that the first step of masonry building design to ensure a stable configuration. Then the masonry whatever the stability is there, it is gained from the supports that is offered by the cross walls, floors, roof, and other elements such as pier or buttresses. Then load bearing walls are the structurally more efficient when the load is uniform distributed and structure is so planned that eccentricity of the loading on the member is very small as possible. To avoid the concentric eccentric loading by providing a adequate bearing of the floor to roof on the walls, providing the adequate stiffness in the slabs, and avoiding the fixity at the supports. So it is especially important in the load bearing walls in particularly multi-story structures are concerned. So this whatever it is there, so carefully it is to be considered during the planning stage of the masonry. So in order to ensure the uniformity of the loading, openings in the wall should not be too large and also should not be a hole in a wall type of as far as possible. The bearing for the lintel and bed blocks under the beam should be liberal in sizes. Heavy concentrated loads should be avoided by proper planning and sections of the load bearing members. As far as it's this one, the commonly occurring causes of the crack is mainly in the masonry is wide variations of the struts in the masonry in the adjoining parts are concerned. So this is all about the basics of the load bearing masonry is concerned.